Hello everyone, this is Sanjay from CSIT branch. Today my AAT Tech Talk topic for web application development is predictive prefetching based on user interaction for web applications. So web prefetching is a key technology to hide network latencies from users. Conventional prefetching methods, however, misconstrue the purpose of the user's browsing behaviors and resulting experience due to their dependency on statistical characteristics or metadata of individual web applications. In this letter, we purpose a predictive prefetching scheme, web prefetcher, which utilizes interaction events to decipher users' genuine intention and context. Our intensive performance analyze the results obtained with the real web browser demonstrate that web prefetcher improves user perceived quality of experience noticeably, outperforming competitive models. Predictive prefetching based on user interaction is a technique employed in a web application to enhance the user by proactively loading and caching resources that are likely to be requested in the future. This approach aims to reduce latency and improve perceived performance by anticipating the user's actions. Interaction monitoring, mouse movements and clicks. Trackers track mouse movements and clicks, tracking user mouse movements and click to understand their behavior and identify pattern. Scrolling, monitoring scrolling behavior to anticipate content that might come into view. So the page analysis, content prediction, analyzing the current page and predicting with which resources like images, scripts and style sheets. So preloading the resources, initiating the loading of predicted resources in the background before the user explicitly requests them. Machine learning algorithms, pattern recognition, using machine learning algorithms to recognize patterns in user behavior and make predictions about future interactions. User profiling, creating user profiles based on historical data to tailor prefetching strategies to individual users. Adaptive prefetching, dynamic adjustment, adapting prefetching strategies in real time based on changes in user behavior or environmental factors. Context awareness, considering contextual information such as device type, network conditions, and user preferences to optimize the prefetching decisions. Resource prioritization, critical resource first, prefetching critical resources such as those required for rendering above the fold content to prioritize the initial page load. Dependency analysis, understanding resources dependencies and prefetching resources that are likely to be needed based on these dependencies. Caching mechanisms, local storage, storing prefetched resources, local storage to minimize subsequent fetch times. Expiration policies, implementing policies to refresh or affect the prefetched resources based on these usage patterns. Asynchronous loading, non-blocking prefetching, ensuring that prefetching activity does not interfere with the user's current interactions, allowing a seamless browsing experience. Feedback mechanisms, users' feedbacks integration, incorporating user feedback to evaluate the effectiveness of prefetching strategies and refine predictions. Performance metrics, monitoring performance metrics such as page load times to assess the impact of prefetching of overall user experience. Web prefetching has been one of the primary techniques to hide network latencies from early stages of the World Wide Web. It helps researchers and developers improve users' web browsing experience by reducing long wait times to download multiple resources accompanied by web applications drastically. Such prefetching techniques can be applied in various contexts including prefetching the next pages. The next piece of content, that is example like article, product or video, or the types of widgets like games. Two components are newly included for web prefetching systems. The prediction engine conjectures future user actions to produce hints on the succeeding requests. Using these hints, the prefetching engine downloads the predicted objects and catches them proactively. Since poor predictions cause the waste of resources at both client and server sides, most of the previous studies have focused on the predicting engine and its model accuracy. Conventional prefetching methods can be classified into two main categories, as described extensively in most of the web prediction algorithms in the literature have been statistical approaches, which utilize object statistics such as temporal locality, popularity, and sequence of requests. However, these algorithms can only generate true predictions using the overall access patterns without any consideration for the user's intentions. The other category covers content-based approaches, where explicit hints are embedded in the hyperlinks or HTTP headers. Such as Such techniques are provided as primitives, which enables modern web browsers to predetermine where to connect or which resources to fetch render in advance. Because these approaches rely on the static information, there are inherent limitations on the responses to users' varying context. Recently, was Gus.js was proposed its latest variant on the context-based methods. It enables a web application to prefetch resources by analyzing visiting popularity data such as Google Analytics. We present a novel web prefetching scheme which reduces users' intention and context based on interaction events occurring during web browsing. The evaluation results show that web prefetcher reduces page load time by 18.4% against the baseline scheme surpasses other models from 5.2 to 12.4. Here is the diagram of overview of this architecture. We analyze the performance gains from the proposed method over various QoE metrics and demonstrate that web prefetchers improves user perceived QoE by 20.7% in terms of speed index, which is known to have the greatest correlation with the actual user perception. So the overall architecture is web prefetcher operates based on series of interaction events triggered by users' browsing behaviors. User interaction events can be utilized for training the basic model. The prediction model is trained offline based on the real-world dataset, which contains the user interaction data of both navigations and clicks, including more than 0.3 million events and 40,000 unique URLs. Specifically, we employed the GRU-based architecture in once the prefetching targets are generated for interaction events, the prefetching engine invokes the browser process to send requests target by target. Note that the modern browsers with multi-process architectures, a browser process handles all the network requests from multiple vendors. When a normal request occurs, the prefetching engine ceases preloading the previous ones and repeats the prefetching procedure for new navigation events simultaneously. Predictive prefetching engine. The predictive prefetching engine is the key part of a prefetcher, where the prefetching is refreshed by interaction event at a time. Each event can either click or navigation for prefetching engine takes different actions according to its types. So these are some of the implementation and how we can set up this. So evaluation of the web prefetching performance. Prior to the analysis of user perceived QoE, we examine the performance of web prefetcher in terms of conventional metric of PLT. Three schemes were considered in the evaluation. The first one is the base. The baseline scheme represents the normal page loading strategy for prefetching. Web prefetcher WP is the proposed prefetching scheme based on the user interaction, and the optimal scheme produces the correct prefetches. So this is the in-depth analysis of QoE metrics. So finally, I can conclude that the web prefetcher, a user interaction prefetching scheme. A prefetcher utilizes the interaction events to construct the user's true intention and context. Our rigorous analysis results not only proved web prefetcher brings a considerable improvement in user perceived UI, but also validate its feasibility for practical use. For future work, we would examine the potential benefits from weighted prefetching. By combining these strategies, web applications can intelligently prefetch and cache resources, creating a smoother and more responsive user experience. However, it's crucial to strike a balance between the benefits of prefetching and the potential downsides, such as increased bandwidth usage and resource connection. Additionally, respecting user privacy and providing options for users to control or disable prefetching is important in implementing a user-centric approach. So these are the references of my topic. Thank you.